In today's lesson, we are going to revisit the power rules and look at a few new different scenarios that we may come across. So they are going to be a little bit more complex. So as things have gone in this course, we kind of start off with the basics and we kind of build off of it and look at more complex examples. And the same is going to be true for power rules. So as a warm-up, we want to simplify each expression, and where possible, we want to evaluate them. So basically, what does it equal? So again, I recommend you trying these on your own. Pause the video, try it on your own. If you don't remember the power rules, please go back and watch or revisit the lessons on the basic power rules, and as well as negative exponents, and try these on your own. So coming back to the examples, this is what we should have. Right? Again, we kind of see the variety of different rules that we could come across. Here in A, we can see that when we divide exponents, when we divide powers, we have to subtract our exponents. We end up with a negative exponent, so we find the reciprocal or flip it, and then we can evaluate it. In B, when we're multiplying exponent or powers, we add the exponents. So 4 plus 3 becomes 7. And again, this we can evaluate because our base, or the large number, is an actual value. C, we have a power to a power. So this means we multiply our exponents. 2 times 3, we get 6. 2 to the power of 6 is 64. Again, make sure a key thing is, remember when you evaluate a power, the exponent does not mean multiply by 2 or multiply by 6. It means you're multiplying the base, or the large number, however many times the exponent is there. One last example I would say, for E, again, multiplying powers together, so we have to add the exponents. We end up with an exponent of 0. And even though this is a base that's a letter or a variable, we should remember the rule that anything to the power of 0 is equal to 1. So even though there is a base there, we can evaluate that because we should know that anything to the power of 0 is 1. Now, all the powers that we've looked at or that we've worked with before have either been an integer, so a value, or a single variable for the base. However, it is possible to have more complicated bases. So for example here, 2p to the power of 3 is an example of a power that we could have. Now to kind of work through this, let's write this in expanded form. So that power of 3 means I have 2p multiplied by itself 3 times. So that's the expanded form. If I want to simplify this, remember we talked about when we're multiplying terms that have letters and numbers, you focus on the numbers. So in this case, 2 times 2 times 2. 2 times 2 is 4, times 2 is 8. And then p times p times p becomes p to the power of 3. So that's the simplified form. So this was our expanded form, and this is our simplified form. Now the brackets are very important because what we just looked at, 2p in brackets to the power of 3, is different than what we see down here of 2p to the power of 3. And the reason that this is different is this one here. The exponent is on the p. So it's only p that's multiplied by itself 3 times, not the 2. In the example that we just did, because of the brackets, that means everything is included when it's multiplied by 3. Or sorry, not multiplied by 3, multiplied by itself 3 times. So let's look at some other examples. So if I look at mn in brackets to the power of 3. If I want to expand this, this just becomes mn times mn times mn. So that bracket multiplied by itself 3 times. Now this is a little bit trickier. We haven't dealt with an example that had 2 variables or 2 letters in it. However, we can treat it the same way that we've been doing the other things. We're going to focus on the parts that are similar. M times M times M. So a variable multiplied by itself 3 times is M cubed. And then N times N times N is N cubed. So same idea. We're putting our M's together and we're putting our N's together. We're not adding them or subtracting them, so we're not collecting like terms. So it's not 3M and 3N, we're multiplying. So that changes the exponent. In the next example, we have a fraction 2/3 to the power of 3. Now I know you may not like fractions, but again, expand it. 2/3 to the power of 3 means it's 2/3 multiplied by itself 3 times. If we want to simplify this, again, when we multiply fractions, we multiply straight across. So our numerators, or the top numbers, all multiplied. So 2 times 2 times 2, which is 8, over 3 times 3 times 3, or 27. And then finally, x over 2 to the power of 4. So we have x over 2 times x over 2 times x over 2 times x over 2. Again, the bracket multiplied by itself 4 times. If I want to simplify this, again with fractions, you multiply the top numbers and then you multiply the bottom numbers separately. X times x times x times x. 4 x's all together, so I can say x to the power of 4. For the bottom, 2 times 2 times 2 times 2, or 4 2's all multiplied together, gives me 16. So this simplifies to x to the power of 4 over 16. Now what we want to note, or what we want to be aware of, is when the base of a power is in brackets, the exponent applies to all parts of the base. So again, you might want to highlight and underline all parts of the base when it's in brackets. So we saw that everything that we multiplied by itself was whatever was in the brackets when the exponent was attached to it. So let's look at these next examples, and it might be helpful to write them out in expanded form first because they might be a little bit confusing. So for A, 10t in brackets to the power of 3. If I'm going to write in expanded form, that means it's 10t times 10t times 10t. 3 10t's all multiplied together. Again, when I'm multiplying terms that have a letter and a variable, or sorry, a letter and a number, I multiply the numbers together. 10 times 10 times 10 is 1,000, and then t times t times t gives me t to the power of 3. The reason I'm putting it right after is because we've talked about it before. When I have a number and a letter joined, the operation between them is multiplying. So I'm still multiplying them together, but I can't simplify it any further than that. For B, 2a over b, all to the power of 4. So again, in expanded form, 2a over b times 2a over b times 2a over b times 2a over b. I have 4 of those brackets together. Again, on the top, I'm going to focus on just the numbers. So 2 times 2 times 2 times 2 is 16. A times A times A times A is A to the power of 4, divided by B times B times B times B, or B to the power of 4. And again, this is as far as I can simplify it. There's nothing I can divide. I can't simplify these two powers because they don't have the same base. For C, 3y to the power of 4 times 3y to the power of 4. Again, because of that squared or that exponent 2, that means there's two of these brackets together. Again, I can multiply the numbers together. 3 times 3 is 9. Y to the power of 4 times y to the power of 4. So I'm going to use my power laws of multiplying powers, which means I have to add the exponents. So 4 plus 4 gives me 8. And then finally for D, this one's a little bit different because I have a number and a base to the power of 2. So the 4 I'm not going to touch because it's not doesn't have the exponent attached to it. It's not included in that bracket. Right? So we're following BEDMAS order of operations. We do the exponent first. I'm going to rewrite it. X over 3 times x over 3. So because of that squared, there's 2 x over 3's. And now I can multiply. I can multiply all of this at once if I want to, and not worry too much about the fractions. Again, 4 as a fraction is 4 over 1. So 4 is the numerator. So 4 times x. Again, 4, there's the only number there. X times x is x squared. And for the denominator, 1 times 3 is 9. So this simplifies to 4x squared over 9. Now, when dealing with negative exponents, so we've dealt with negative exponents before, and when we recall negative exponents, they represent division or the reciprocal of a power. So basically that just meant that we flipped it. So we flipped our exponent or our base. So let's consider the fraction 3 halves, or 3 over 2, all to the power of negative 3. Now, we could rewrite it to get a positive exponent of 1 over 3 halves, or 3 over 2, to the power of 3. So 1 divided by 3 halves to the power of 3. But when we divide fractions, so 1 divided by 3 over 2, let's just say we don't have the exponent there. What would happen is this becomes 1 multiplied by 2 over 3. Right? We change it to multiplication and we switch the sign. Or sorry, switch the numbers. So the same idea applies here. Because if we want to turn this exponent into a positive, we would have to divide it or put it underneath 1. Basically, it works out to just flipping the fraction. And that would change the power of the exponent. So instead of having to write 1 over 3 to the power of, or 3 over 2 to the power of 3, we can just write 2 over 3 to the power of 3. And again, what we talked about, if I wanted to write it in expanded form, 2 over 3 times 2 over 3 times 2 over 3, which works out to 8 to the power of 8 over 27. So there's multiple rules here. If we have a fraction in our bracket and it's to a negative exponent, in order to turn it to a positive exponent, we just flip the fraction. So before, when we had a negative exponent, we had a whole number, we were to put it over 1. But if you turned a whole number into a fraction, that's basically flipping the fraction when we put it underneath 1. The other rule that's included in this is that if I have multiple things inside a bracket that has an exponent on it, that exponent applies to both parts. So that's what we're seeing here. This n, or exponent n, is applying to the b as well as the a. So anytime you have multiple things inside the bracket, that exponent applies to all of it. So let's put it all together. Let's simplify our expressions where we can. So x to the power of 5 times x to the power of 3 to the power of 2. So this has multiple power laws. I'm going to follow the order of operations. I'm going to do the exponent first before I worry about multiplying. So x to the power of 3 to the power of 2. This means I have to multiply my exponents, so it becomes x to the power of 6 times x to the power of 5. Then I add my exponents because I'm multiplying powers. This becomes x to the power of 11. For b, I have a squared b cubed times a to the power of 5 times b to the power of 4. Now, this is a tricky one. We haven't seen this before, but again, we're going to treat it the same way when we've had multiple things multiplied by another set. We're going to focus on the parts that are the same. So I'm going to focus on the a squareds, the a's, because they have the same base, and I'll leave the b's or focus on the b's second, because again, they have the same base. So a squared times a to the power of 5. This rule is, when I multiply powers, I have to add exponents, so this becomes a to the power of 7. For the second one, for b's, I'm going to focus on, again, b to the power of 3 times b to the power of 4. The rule is, when I multiply powers, I add the exponents, so this becomes b to the power of 7 as well. And that's as simple as it can get. For c, this is an example where I have multiple things inside the bracket with an exponent on it. And we've talked about that this exponent applies to both the 3 and the y squared. So that 3 goes to the 3, that exponent 3 goes on the 3, so we can say 3 to the power of 3. For y, we have to use our power law because we see this exponent here. So y to the power of 2 to the power of 3. I have to multiply, so this becomes y to the power of 6. And I can simplify the number because I can do 3 to the power of 3 and get 27, and then y to the power of 6 just stays the same. For d again is another complicated one, but again, I'm going to focus on what I know, or focus on the parts that are similar. So in this case, I'm going to focus on just the numbers in front. 4 times 3 times 2. 4 times 3 is 12, times 2 is 24. And secondly, I'm going to focus on the powers with the base k. Because I'm multiplying them, I have to add the exponents. This becomes k to the power of 2 plus 3 is 5, minus 4 is 1. Or I can just write it as 24k. I don't need to show the exponent 1 because if we don't see an exponent, we assume that it's 1. For e, again, another fraction with an exponent. It's a positive exponent, so I don't have to worry about it too much. But what I can do is, instead of writing in expanded form, I can say, well, that exponent of 3 applies to both the 3 and the 4. So this is the same way of saying 3 to the power of 3 over 4 to the power of 3. This I can simplify and get 27 over 64. And if you're not quite sure, you can expand it. 3 over 4 times 3 over 4 times 3 over 4. And you should get 27 over 64. In f, again, multiple things going on here. We have a number and a variable in brackets, and then we have exponents attached to that. What we're going to do first, again, still follow order of operations. I'm going to deal with the exponent first. The only exponent I can deal with is this 2 here. I can't work with that 3. There's nothing I can do. I can't simplify n to the power of 3. However, I can simplify this exponent outside of the bracket by applying it to both the 2 and the 3. So this becomes 2 to the power of 2. And n, because it's a power to a power, 3 times 2 becomes n to the power of 6. I can simplify 2 to the power of 2. 4n is still staying there. 2 to the power of 2 is 4. N to the power of 6. And again, when I have letters and numbers, I'm going to focus on just the numbers and then just the letters and just the letters that are the same. 4 times 4 is 16. N to the power of 1, we could say, times n to the power of 6. We need to add our exponents. 1 plus 6 is 7. For G, w to the power of 5 times w to the power of 3 divided by w to the power of 4 and times w to the power of 6. So again, multiple things here. Simplify the top first, and then simplify the bottom, and then worry about the division. Again, it's multiplying powers, so I add the exponents. W to the power of 8 over w to the power of 10. This becomes w to the power of negative 2. To get it as positive, I flip it, and it becomes 1 over w squared. For h looks very complicated, but if we stick to what we've dealt with when we have multiple things, it should be okay. And the rule is, focus on the parts that are the same, or focus in this case on the powers that have the same base. So the x's, focus on them together, the y's, and the z's. Because it's all division, I can't do anything to simplify the top and the bottom. They're all different letters. So I'm going to focus on the division. Division of powers means subtraction. Subtract the exponents. So x to the power of 3 divided by x to the power of 1. 3 minus 1 becomes x. Becomes x to the power of 2. Y to the power of 2 divided by y to the power of 3, or 2 minus 3 is negative 1. And then lastly, z to the power of 4 divided by z to the power of 2. 4 minus 2 is 2. So we have x squared, y to the power of negative 1, and z squared. Now, we don't want negative exponents generally, so I do have to flip that fraction, or flip y. I could say 1 over y to the power of 1, or 1 over y. But if I'm multiplying, if I turn all of these into fractions, the whole numbers just have 1. In the end, what I'm going to get is x squared on top. So x squared times 1 times z squared. X squared, z squared, 1 times y times 1 is just divided by y. For I, 1 over y to the power of 3, all to the power of negative 2. We've talked about when I have a fraction with a negative exponent, I just flip my fraction. So this becomes y to the power of 3. You could say over 1, but it doesn't really change anything. And this exponent now becomes positive. This is a straightforward power to a power. So this becomes y to the power of 3 times 2, which is 6. For j, again, multiple things going on here. I have a negative 3a squared divided by b, all to the power of 3. So this one is complicated. We do have to think that there is a negative 1 here. So this 3, or exponent of 3, applies to the negative 1. Or actually, yes, there's a negative 1 there. No, yep, sorry, my mistake. Yep, we can still apply it. Applies it to the negative 1, applies it to the 3, applies it to the a squared, and applies it to the b. So negative 1 to the power of 3, and times 3 to the power of 3, times a squared to the power of 3, power to a power, multiply a to the power of 6, and then divided by b to the power of 3. Now I just need to simplify a bit. I can do negative 1 to the power of 3. That's just negative 1, or there's a negative out front. 3 to the power of 3 is 27. A6 is already done, and divided by B3 is also already done. I can't subtract these exponents because the bases aren't the same. So again, remember the base or the large number of your exponent must be the same in order for the power rules to work. For k, now I have an actual fraction with a negative exponent. In order to get a positive exponent, I flip my fraction, so it becomes 4 over 5 to the power of positive 2. But again, we need to keep in mind that this exponent 2 applies now both to the 4 and the 5, even though it was the same thing before. It did also do that. So you could say as 4 to the power of 2 divided by 5 to the power of 2, or you could, and then you could simplify to 16 over 25. Lastly, for L, 6w cubed minus 6w squared cubed times negative 2w squared divided by 4w7. Again, I'm going to simplify the top first. So 6 times negative 2, I'm going to focus on the parts that are the same. 6 times negative 2 is negative 12. I'm then going to focus on the letters or the powers with the same base. W to the power of 3 times W to the power of 2. Add my exponents, this becomes W to the power of 5. Divided by 4W to the power of 7. Now, finally, I have just a single term on top and a single term on the bottom. I'm going to go through the same steps. Focus on just the numbers and just the powers with the same base. So negative 12 divided by 4 is negative 3. W to the power of 5 divided by W to the power of 7. You get W to the power of negative 2, which then turns into negative 3 over W squared. You could look at it and say, well, I have 5 W's on top and I have 7 on the bottom. That means in the end, I'm going to end up with 2 W's on the bottom. Right? So that's another way you could think of it as well, but without going to the negative exponent and then flipping it back. So in this lesson, again, we're using the same power laws that we've dealt with in the past. We've added in a scenario where we have a fraction with a negative exponent, as well as what happens when we have multiple things inside the bracket and it's all set to a certain power. And basically it just means that that exponent applies or gets attached to everything inside the bracket. Now this may mean you need to use power laws in order to do that, but we've looked at examples of that. And again, this will be as complicated as exponents get in this course. If you are a bit unsure of the power laws, please make sure you go back to the previous lessons that looked on those and touched on the more basic rules to help refresh your memory for this lesson.